Welcome back to the class on a power semi-connected drives. In this class, we are going to discuss about the analysis of a first quadrant operation of a DC shunt motor with a DC to DC converter. Already we know that the first quadrant operation is nothing but a motoring operation, where the load voltage and current is the positive. In this class, we are going to find out what is the expression for the minimum value of the load current and maximum value of the load current, because we have taken the load current as a continuous load current. In case of first quadrant operation, when the switch is closed, the supply is directly connected to the motor, armature of a DC motor. This armature we can represent it with a RLE load, resistance, inductance, as well as back EMF, RLE. Now you apply the KVL in this code. Sum of the voltage drop across the resistance, inductance, and EV, that is equal to the applied voltage. When the switch is on, the load current is changing from the minimum value to the maximum value. When the switch is off, the current is changing from the maximum value to the minimum value. This is one cyclic operation. The same thing will be repeating for the remaining cycles also. Now, when you apply the KVL in this loop, you are getting the input voltage equal to the voltage drop across the resistance and the voltage across the inductance is nothing but L into di by dt plus dt. Now, EB is a constant, take this side. V minus EB equal to R into I of t plus L into I of t dt plus, here EB is not there. Now, this is the equation between the t greater than the 0 and less than the t on. Take the Laplace transformation both sides. So this is a constant. So V minus EB by S equal to R into I of S plus the Laplace transformation of the derivative becomes L into S into I of S minus initial value of the current. When t equal to 0, the initial value of current is the I minimum. So in place of I of 0, we have taken as a I minimum. That we are substituting here. V minus EB by S equal to R into I of S plus L into S into I of S minus AM. Now we are going to find out the value of IS. Take the IS common. R plus SL minus L into I minimum. Take this term also right hand side. So V minus EB by S plus L into I minimum equal to I of S into R plus SL. Now take this term this side. So finally we're getting the I of S equal to V minus EB by S into R plus SL plus L into I minimum by R plus SL. The denominator take the common L. So this equation will be rearranged in this manner. Here, whenever you have taken the L common here, this denominator and numerator will get cancelled. Numerator will get in the I minimum. If we take the inverse Laplace transformation for this equation, we are getting the I of t equal to V minus EB by R into 1 minus e to the power of minus t by ta plus L minimum into e to the power of minus t by ta, where ta equal to L by R, nothing but a time constant of the load, where L is nothing but a inductance of armature winding, R is nothing but a resistance of a armature winding of a DC. Again, we have taken the same equation what we have derived previously. I of t equal to V minus EB by R into 1 minus e to the power of minus t by ta plus L I minimum into e to the power of minus t by ta. Here. So now we are applying the final boundary conditions. Final boundary conditions are nothing but a t equal to t on. I of t equal to I maximum. I of t, you take the I maximum. In place of t, wherever the t is there, you take the t on. So finally, you're getting the I maximum equal to V minus EB by R into 1 minus e to the power of minus t on by ta plus L into I minimum to e to the power of minus t on by ta. This is the equation 1. This is the first equation, what we got it by applying the KVL when the switch is in the on condition. The same manner, we are again applying the KVL to the circuit when the switch is in a off condition. When switch in off condition, there is a freewheeling action taken place. So the sum of the voltage drop across the resistance, inductance, and EB equal to 0. In this interval, the current is changing from the maximum value to the minimum value. So This is the voltage drop across the resistance. This is the voltage drop across the inductance. This is the EV. Now here we define the new variable, that is the T dash. The T dash will be starting from this point and ended at this point. Now what is the difference between the T and the T dash means? The starting point for the T is the 0, whereas the starting point for the T dash is the T on. See here we have written the condition. Greater than or equal to T on, less than or equal to the T. Now take the EB this side. We are getting the minus EB equal to R into I of T dash plus L into di of T dash by dt. Take the Laplace transformation. Minus EB by S equal to R into I of S plus L into S into I of S minus I minimum I of 0. Nothing but what is the value of current at this point? That is nothing but a maximum. So in place of I of 0, you substitute the I maximum. You are getting the minus EB by S equal to I of S into R plus L into S into I of S minus L into I maximum. We bring this term to the right hand side. We are getting the I of S equal to L into I maximum by R plus Ls minus EB by S into R plus Ls. Now in the denominator you take the L common. In the first term, whenever you are taking the L common, that will be cancelling with a numerator L. So we are getting I of S equal to I maximum by R by L plus S minus EB by Ls into R by L plus. Now you take the inverse Laplace transformation for the above equation. We are getting the I of T dash equal to I maximum into e to the power of minus T dash by Ta minus EB by R into 1 minus e to the power of minus T dash by Ra. Now here we are defining the T dash equal to T minus T on. Now we are going to apply the final boundary conditions. Nothing but when T equal to capital T, now the T dash equal to T of, now the I of T dash equal to I minimum. Now you are substituting all these values in the above equation. You are getting the I minimum equal to I maximum into e to the power of minus T of by Ta minus EB by R into 1 minus e to the power of minus T of by T. We know that T equal to T on plus T of, where T of equal to T minus T on. So in place of T of, we substitute the T minus T on. We are getting the I minimum equal to I maximum into e to the power of minus T on divided by Ta minus EB by R into 1 minus e to the power of minus of T minus T on divided by Ta. This is the equation 2. We got this equation when you apply the KVL when the switch is in off condition. Now we got a one equation when the switch is in on condition. Now this is the second equation. Both equations in terms of I maximum and I minimum. So by means of these two equations, if you solve for the I maximum I minimum, you're getting the I minimum equal to V by R into e to the power of T on by Ta minus 1 divided by e to the power of T by Ta minus 1 minus E by R. I maximum equal to V by R into 1 minus e to the power of T on by Ta divided by 1 minus e to the power of T by T on minus E by R. So in this manner, you have to find out what is the expression for the minimum value of the load current as well as the maximum value of the load current.